Okay, hello everybody. If you've enjoyed talks on rodents so far, you're going to love more talks on rodents. So this is a bit of research that came out of the final research chapter of my PhD, which is looking into the biomechanical significance of the big, long internal length of the incisor root as we see it in rodents and a couple of other non-rodent diprotodonts. So we're trying to figure out what the biomechanical significance of having something that goes quite so far back in some specimens as to almost go right into the condyle. Does that play some sort of role in strengthening the mandible during that typical rodent behavior, which is gnawing at things? So from the very beginning, rodents are an order of mammals that are characterized by their distinct masticatory apparatus, and that itself is characterized by this long pair of continually growing incisors, which is called a condition called diprotodonty, and these are separated from a set of reduced cheek teeth by a large diastema. Rodent ecologies are also incredibly diverse, and rodents inhabit almost every terrestrial environment on the planet and occupy every continent on the planet apart from Antarctica. And likewise, they also show huge ranges in their body size and ecologies, such as ranging from very, very tiny right up to really quite large in some fossil specimens here, like Josephordigasium manisi. We also see this rodent-like masticatory apparatus, so diprotodonty most especially, in a series of non-rodent diprotodonts, including some fossil specimens such as diprotodon, the marsupial, and some extant ones, including the common wombat, the ii, and the hyraces. And you can see that these are all showing these distinctive incisors, diastema, reduced cheek teeth. So going straight into what diprotodonty really is, as I say, it's a pair of typically long curved incisors, and you can see here that the root length of these specimens is pretty long, so, often going right past the molar row and sometimes just sitting beneath it, but often getting right up into the coronoid or condyle, depending on which specimens you're looking at. They're curved, they're continuously growing, and because they're continuously growing, they're technically rootless, but for the sake of this talk, I'm just going to refer to any material posterior of the alveolar margin as the root, just because it makes it easier. And they use sharp chisel-like blades to do that gnawing behavior that I referenced. And if they don't sharpen their blades regularly, then you end up occasionally with pathologies like this, which often kill the specimen or end up with breaking. It's not what you want. A series of features related to bending resistance we found in previous chapters of my thesis. Those features related to bending resistance, such as a large second moment of area, have been shown to scale with the length of the bending moment. Now, the length of the bending moment then is going to be the external length of the incisor, so anything sticking out of the alveolus. We also found that the internal length of the incisor relates to this external length of the incisor. So how deep the root goes, to a degree, varies with how much incisor is sticking out of the mandible. And it's been demonstrated that that a long incisor root on some of these specimens is to dissipate the stresses and strains encountered during incision along the length of the incisor and distribute those forces across the mandible, thus strengthening the mandible during incision. Another feature that's been suggested to do a similar sort of thing is the development of an arch-like shape of the mandible. Now, this arch here has been suggested by Jasinski to be a result of the curved incisor growth, and creating an arched-like mandible. The biomechanical significance of that sort of structure would be to reduce the size of the bending moment by about 25%. So overall, we've got a few different features which are coming together to create a structure that is functionally very strong for dealing with biting at the incisors. And the key focus of this study here is to explore, well, what happens if we start to shorten those incisor roots? Does that change increase the amount of strains that the mandible is encountering during incision? So our first hypothesis is that by virtually modeling to reduce the internal length of the incisor root, we'll start to see an increase in strains across the mandible. We also hypothesized that the non-rodent diprotodont, in this case we're using an ii, will fit into the range of variation observed in rodents, and that's based off of some previous studies that we've shown where the ii is showing itself to be very rodent-like in a lot of its structures. But what happens if we don't really find there's a huge increase in strain as soon as we start shortening that incisor root? Well, it might be that the area where the incisor grows is generally under lower strain. That could be the reason why you can have a material like that, which is continuously growing so deep inside the root. And our hypothesis is that if that's the case, when we examine the mandible in cross-section with the incisor root now removed, the area around that incisor should be experiencing quite low strains. So we'll explore that later. The sample we're using is a series of 4 rodents, grey squirrel, crested porcupine, North American beaver, brown rat, and then a non-rodent diprotodon, once again, the II. And we're going to be using finite element analysis to explore the deformations and the strains experienced by these specimens during incisal biting at different lengths of incisal root. So FEA, well, we've had a couple of talks talk about it today, produced a series of models using micro CTs, imported those into a voxel-based finite element software, VoxFE, and we get an output like this, which produces a series of contour maps, and we can also extract strains and the like to explore how the structure is dealing with the forces it's encountering. So, the way that we actually went about shortening the incisors is all this material that is outside the past the alveolar margin, we don't want to alter because that represents the length of the bending arm. We are interested, however, in changing this internal root length. And so we produced 5 models in total. The first model would have a full incisor length, totally unmodified. Then we'd have another one where it had its internal length reduced to about half, so from about here in this area have been replaced now with a material equivalent to cortical bone. And then we do the same again, but now with a length down to quarter internal length. We then made 2 more models, once again down to half and quarter length, but the area where we had filled it with cortical bone, or where the incisor used to be, has just been left full of air. So nothing going on there, just totally removed material. So here's the impact of doing that. If we look at things from a variety, from the lateral and the dorsal view, it doesn't look, as we move from full length down to half length, quarter length, like a great deal is actually happening when we are shortening these internal incisor lengths. But if we take a look at it from the ventral view, and it's a bit hard to see actually on the screen, but from full length to half length, you can immediately see a boundary separating the more stiff incisor material and then the strains increasing now that it's dealing with a softer cortical bone. And then the same thing happens again, but even more so now, removing that area of resistance, I suppose you'd say, where now that we're down to quarter length and the incisor is basically up in here somewhere. And then those trends again are increased when we move to the hollow models, though that's not immediately clear from the contour plots. So to take a look at that in more detail, we placed a series of landmarks along the ventral surface of the mandible following the external surface of where the crypt would have been, and extracted the strains along there. Initially, you can see that along the symphysis, there's quite high strains, but as soon as we start to reach this thicker area of bone along the actual body of the mandible, I suppose you'd say, strains drop right down. But then strains start to go back up again at the point where we've started to remove incisor material. Occasionally, so with this blue line here representing the original full-length incisor, we have almost a doubling of strains in the models where that material has now been removed. That supports our first hypothesis that the removal of internal incisor length increases the amount of strains experienced through the mandible. This suggests that maybe there's something going on here, that this internal incisor plays a role in the strengthening of the mandible during a bilateral incisor bite, which is what we've modeled on all of these. And that pattern is continuous across all of our sample. In particular, it's worth paying attention to Dabentonia madagascarensis, the II, which continues to show the same pattern of hugely increasing strain once we take away some of the internal length. The way that the II separates itself from the rest of the sample, however, is in the sheer magnitude of strains that it's experiencing. For most of these, you can see around 180, 450 microstrains, whereas up to here, we're looking at about 1,200. across all the specimens, most of our sample only experienced an increase in strain of about 14% when we shortened it down to the quarter length. The II experiences an increase in strain of 35%. And that's probably due to the sheer amount of incisor material that makes up the overall volume of the incisor, which here is about 20% of the whole mandible is incisor. And that then suggests that we cannot necessarily support our second hypothesis, that the non-protodon II follows entirely the same pattern as the rodents that it's associated with. Now, since we haven't seen a great deal of increase in strain, really 14% is not a gigantic amount to suggest to explain the sheer quantity of incisor material that we're seeing in some of these specimens. It's worth paying attention to maybe the incisor is, as we've suggested earlier, in an area of generally low strain. So what we have here, this is a cross-section taken just past the molar row in all specimens. This area has now been filled with cortical bone. These are the quarter-length shortened models. And if we look at hystrix, this is the area where the incisor root would have been. It's somewhat low in strain, but it's not really producing a clear path or area of distinct low strain where that incisor root used to be. And across all these other specimens, that continues to be the case. And if you move along the slices in, say, a viso or something, and looking at the increase in strain, the area where the incisor would have grown is by no means clear. So it appears to suggest that the incisor somewhat grows in an area of low strain, but it does not coincide, or those two things do not inform one another. So the significance of all this, with the reduction in length of the incisor root, we see an increase in strain across the mandible. The area where the incisor has been reduced and the crypt left solid, we experience lower strains in that area immediately around it, but the path that the incisor would have taken is not immediately apparent. And that the non-rodent diprotodon II experienced an increase in strains, but much like the rest of the rodent sample, but the sheer quantity of strains experienced are more than double that experienced by even the closest other rodent. So the general take-home message from this study is that as you remove, if you have a model of solid cortical bone of a relatively less stiff material filled with a body of a stiff material, as you remove that stiffer material and leave the other loading conditions the same, strains go up. So this suggests that the rodent-like deep root incisor plays some role in the mitigating of the stresses encountered during incision. Thank you very much. This talk's been, I was able to attend thanks to the Jones Fending Memorial Fund. Thank you to the following people for the production of specimens for me, and special thanks also go to my supervisors, Phil and Sam, who've put up with me for the last 4 years. Thank you very much. Are there any questions?